announcements. So as you know, this talk, as well as all the previous talks, are being recorded. So you're going to be able to watch the all the previous talks are going to be on our YouTube channel to be posted shortly at the chat. Also, if you'd like to subscribe to our mailing list to receive the announcements for the future webinars, please send webinar to our email or to this WhatsApp number that you find on the chat, and advertise as much as you'd like. We also have the future schedule. So we have quite a few talks scheduled every week, alternatingly on Thursdays and Fridays. So next week it's going to be on Thursday, always at the same time. Andres is going to post shortly the link to our YouTube channel. There it is. So you can catch up with all the previous talks over there. So without further ado, let's hear about integrality for Frobenius manifolds. Please, Alex.
Okay. So let me first thank the organizers for the invitation to give a talk in the seminar, especially Enrique. And I'm very happy to talk here. I mean, this very great initiative of having this South American seminar. I mean, putting together people interested in geometry. So, okay, my topic today is integrality for Frobenius manifolds. So let me start saying in a few words what a Frobenius manifold is in a very short word. So you have this tuple of M. So you can consider M as a complex manifold. So you have this circle, this is a product on the tangent bundle, and you have also this G-flat metric and a distinguished Euler vector field. And actually, the point of the definition is that this algebra actually, this product here, this algebra actually has a bilinear form, and non-degenerate symmetric bilinear form. And it makes this algebra actually a Frobenius algebra. This is why these manifolds are called Frobenius manifolds, because we have this structure of Frobenius algebra in the tangent space. And actually, this is, I mean, this G actually, this flat metric on the manifold actually is coming from this bilinear form from the product. And okay, it should satisfy some axioms. There's a list of actions that they should satisfy, but actually the best thing actually to approach these things would be with examples, and I will give some examples of the notion in a second. Let me just say that this is this object was actually introduced by Dubrovin as kind of geometric solution for WDBV equations, but also you can actually find in other works, in previous work by Saito in singularity theory, for example, you can find some idea of Frobenius manifold, but with this name actually comes from the 90s in the works of Dubrovin, right? So, good. So for the goal of today, there are three main sources of examples. One of the examples come from quantum cohomology for finite manifolds, for example, projective spaces or Grassmannians. Essentially, quantum cohomology is a kind of it's a deformation of the usual cohomology of the manifold. Actually, the name is a little bit misleading in the sense that this is not really quantum and it's not cohomology at all. It's not cohomology in the strict sense because it's not functorial, for example. And the ring you get actually is commutative ring, so it's not really quantum. But for some reason, actually, it was named quantum cohomology. But this is a deformation of the cohomology ring. I will actually give some example of this thing later, probably. And the other source of examples comes from singularity theory. Is the main example there is the unfolding of AD singularities. You consider this space of the unfolding of AD singularities, and the third one comes from the geometry of Hurwitz spaces. In particular, there is one nice cases of this example, which are these modular Frobenius manifolds. In particular, in dimension 3, this is related with some chassis equations. They are kind of modular, comes from the fact that there is a way to define this Frobenius manifold using the potential, and in this case, the non-classical part of the potential actually is some function which satisfies the chassis equations, and you know that these solutions are generated by quasi-modular forms. That's the reason modular in this name, and there are kind of arithmetic properties for this type of Frobenius manifolds, which are quite interesting. And then actually these three examples. Oh, this should. Okay, I didn't say that, but okay, these three examples actually are the case of semi-simple Frobenius manifolds. Probably you're quite familiar with, for example, Calabi-Yau manifolds, and you know, quantum cohomology and Gromov-Witten theory for Calabi-Yau manifold. This is not the case I consider here. I mean, Calabi-Yau is not semi-simple, but somehow it's orthogonal if you want to the cases I want to consider here, and then actually it will be clear why I'm interested in the non-semi-simple cases. Okay. The first, one of the main objects actually in the definition of the Frobenius manifold is what is called the first structure connection for the Frobenius manifold. And what is the first structure connection? Which is actually a flat connection. So with singularities in the pullback of the tangent bundle, and it's actually given by this. It's given by this formula here. Here, this is actually this nabla x is the Levitch beta connection on M, and this actually lambda is a parameter in P1, and this is the product. Actually, this is the quantum product, or this is the product of the Frobenius manifold, if you want. And this is also known as kind of extended connection. And actually, here is a typo. This is not in the. This should not be lambda, but probably here it should be in the lambda direction, right? Not in the set direction. The lambda direction. So in the lambda direction, actually, we get this equation, and this connection is, in fact, the main actor of the talk today. This is the main object I want to discuss today. And as this part of the connection is actually the multiplication by the Euler vector field. Just remember, I said that this is part of the data, that there is this distinguished vector field, and then we have here this multiplication by the Euler vector field, and this is a matrix. This is a diagonal matrix. We can construct some gradient operator, which is actually not so important. I will give an example of this in the case of quantum cohomology for projective spaces, and I think this will be clear, right? And okay, here this should be lambda also, not set. Sorry. And the important point is that, and okay, one thing I didn't say, that this is actually this connection. It makes sense in the semi-simple case. You are not in the semi-simple case. This lambda direction is not actually relevant. It doesn't appear actually. I'll say, for example, in the case of quantum cohomology, it will be clear why this doesn't make sense in the non-semi-simple case.
Alex, just a quick question.
Good.
Can you just give an example of what this product looks like?
I will. In the next slide, I will.
Okay. Cheers.
In the next slide, I will. Right. And then actually, the important point is that actually I want to focus in in this equation, because when you actually restrict to this fiber, this becomes actually a differential equation with two singular points. Singularity, some regular point at 0 and some irregular point at infinity actually is a pole of order 2. And that's the important thing. And actually, I want to discuss why this is the important thing. So now let me make an example for this Frobenius manifold and this product, right? So the main example, probably the canonical example, let's say, is the case of projective spaces. So we have these projective spaces of dimension k minus 1. You have this standard basis for the cohomology, so you can think this is actually the hyperplane class. So you know that actually the cohomology ring is generated by the hyperplane class. So we have this basis. And then in that case, you have this product. In the case of the quantum cohomology, the Euler vector field actually is the Fertian class. So you have the quantum multiplication by the Fertian class. And the matrix multiplication by the Fertian class looks like this in the case of the quantum cohomology. So you always can describe the product in terms of a matrix. So for the case of projective spaces, this product by the Euler vector field, which is the Fertian class in this case, looks like this matrix. And then actually the graded operator is just this diagonal matrix here, right? So I don't know if this actually answer your question, Enrique, or maybe you want more explicit discussion about the product.
I mean, how does this act on vectors? Just by matrix multiplication.
You mean somehow you have to give this, but you have actually to give this.
Right. What's the representation
for this thing, and use the matrix multiplication? I mean the usual multiplication of matrices, right?
Okay. Cool.
Right. It's the usual multiplication of matrices, right? Exactly. So the point is that actually I didn't set that up because it's quite confusing. The point is that you have here, for example, in quantum homology, you have the ring, and you actually can describe this. You can consider this connection out of the ring, and actually this is somehow the quantum object in some sense, because what you get is some D module, which is not non-commutative object, right? And you can actually write this connection as a matrix differential equation, and you have this interpretation of the quantum product in terms of this equation and using this multiplication by the Euler vector field. But in this case, it's just the matrix multiplication, right? Okay.
Okay, cool.
Okay, this is the canonical example, the canonical example of this Frobenius manifolds, right? And I mean, for the rest of the talk, it's enough if you focus on this example. I mean, if you consider this example, this is enough for today. In some sense, what I want to say is this: in the cases I want to consider today are actually formally this case in some sense. I hope to make clear that point there. Okay. So what is the problems we have with this thing? So I said that the important thing is we have this differential equation here, this connection with these two singular points. And actually, I want to study what happened with this differential equation, because why we are interested in the differential equation, because in some sense, I mean, the monodromy data of this equation is kind of local data for reconstruct the Frobenius manifold. So morally, we can reconstruct the Frobenius manifold using this, gluing this monodromy data. So here, actually, we have that because we have this irregular point, so we have the Stokes phenomenon. So if we want to study this differential equation around this irregular point, we have the Stokes phenomenon. This means actually that the solution of the equation, they don't live in the plane but in sectors, and we want to see how the solutions are related when two sectors are overlap. I mean, when two sectors overlap, we want to see how is the behavior of the solutions, and actually two solutions are related with, which is ordered by certain matrix, and this is the Stokes matrix. And that data actually is one of the things we want to compute for these Frobenius manifolds. So that's the first problem here is to compute the Stokes matrix, because they are part of the monodromy data for Frobenius manifolds, and in the semi-simple case, it has these Stokes matrices. They have a lot of information about the Frobenius manifold, and then the second question is, when are Stokes matrices integral? So in principle, if you compute these matrices from the purely point of view of differential equations, you don't expect to have integral matrices, because you're going to expect some matrix with complex entries. But it turns out in computation that you get integral Stokes matrices. So the question is, when you have this integrality property, and actually this question is important for Dubrovin conjecture and Gammon conjectures. I will back to Dubrovin and Gammon conjectures at the end of the talk. So for the moment, it's not really important what these conjectures are, but I will back to them. And the second part of this second question is, what is the meaning of the integrality? So why we get some integral Stokes matrices? Again, from the point of view of differential equation, this is a little bit strange, because there is no a priori reason to have integral numbers there. But because of the geometry behind these Frobenius manifolds, this integrality became natural in some sense. But still, this is a question about the meaning of the integrality, and the goal of this talk is try to avoid this question and try to give some ideas or some insights about what the integrality would mean in this setting of Frobenius manifolds. For the case of quantum cohomology, there is some deep studies about the integrality condition, and actually I will use these works about integrality for the quantum cohomology to formulate some ideas of how to extend integrality for quantum cohomology to other types of Frobenius manifold. That's the goal of this talk, right? So, any questions so far?
Maybe I can ask. So Q is just a form of variable, right? You probably want to expand in Q. What is Q?
Which one?
In the lower left, in the last row. No, on the matrix. What's
this Q? Yeah, exactly. This Q is exactly. This Q is the somehow the quantum parameter, is the parameter of the deformation, right? Yes. So
right.
Somehow the point is that what is the quantum cohomology ring of this thing? So the cohomology ring of this is the polynomial ring, right? In one variable, and the relation is x k equal to 0, right? So when you have the quantum cohomology ring, you add this parameter Q, and what you have in the cohomology is C x Q, and now the relation is x k equal to Q, right? And that's the Q here. Is the quantum is somehow the parameter of the formation, right?
Okay, cool. Thanks. Yeah.
Exactly.
I want to ask something.
Okay,
too.
good.
What does mean semi-simple in this context that you are talking, and why does this computation doesn't work in the other case?
That's a good question. Semi-simple means that you have these algebras in the tangent bundle, right? So this means that they are semi-simple as an algebras. So actually, this means that if you look at this algebra, they are direct sums of fields, for example, complex fields, right? They are semi-simple as an algebras. But you have, for example, when you have actually the Calabi-Yau case, and you have the product there, they are not semi-simple. You decompose the algebra, they are not semi-simple. But actually, your question is really important, because I mentioned Dubrovin conjecture here. Actually, Dubrovin conjecture here is about semi-simplicity. It's related with what semi-simplicity would mean in terms of some derived category stuff. And I will back to the question of the semi-simplicity, because it's really important, actually. It's really, really important, the semi-simplicity, because it's actually the content of the Dubrovin conjecture, right?
Okay, thank you.
The definition of the semi-simplicity is the algebras are semi-simple, it's an algebras, right? So this means they are direct sum of fields. So I mean, the complex field in this case, you can consider this as a complex. Well, everything you can consider over the complex numbers, so that's okay, right? There is other questions? No. Okay.
We're good.
Sorry.
I think we're good. Let's proceed.
I will continue. So let me actually go in a bit to physics in some sense. There is this paper by Cecotti and Vafa. It's actually a paper. It's actually 92. The paper was actually the archived version is in 92 probably. And in that paper, actually, they proposed this problem to classify n equal to supersymmetric models. And they actually wanted to classify these supersymmetric theories, and then the method that they used was study the so-called TT star equations. And the problem actually is reduced to the problem I have here: is find all integral strictly upper triangular matrices of size n, such that the eigenvalues of this matrix here belong to the unit circle. So they want to classify some integral matrices, triangular matrices, and then so how the classification of these matrices is the classification of these theories. Those matrices actually they want to classify are the Stokes matrices for the TT star equation. So that's what they want. So the main goal of the paper by Cecotti and Vafa, in some kind of more sophisticated words, is actually to find solutions of some differential equation is now known as the total lattice with opposite signs, whose actually semi-infinite variation of a structure has set structure. So essentially that means that you want to find the Stokes matrices for these TT star equations and see if the entries of the Stokes matrices are integral. That's the problem for Cecotti and Vafa, right? Actually, there is this theorem. It's not really a theorem. It's this kind of folklore result. I mean, it should be proven that the Stokes matrices for the TT star equations and the Stokes matrices for the the associated Frobenius manifold are equal. In some sense, the Frobenius manifolds are the holomorphic part of the TT star equation. So you get, and if you look at this Stokes matrices for the Frobenius manifolds and you compute the Stokes matrices for the Frobenius manifolds, then you actually get the Frobenius manifold for the Stokes matrices. So in that sense, this problem by Cecotti and Vafa can be reformulated in the problem of find the Stokes matrices for some Frobenius manifolds and look at the integral Stokes matrices. That's actually the problem, this problem here. So we want to compute some Stokes matrices for some Frobenius manifold and look at the integral Stokes matrices. And we have this relation with this supersymmetric theories, right? In their paper, Cecotti and Vafa classify completely the equation for dimension 1, 2, and 3. And for higher dimensions, the problem actually is still open, how to get all the solutions. And I will discuss one of the cases because, as mentioned at the beginning, there are 3 sources of examples of Frobenius manifolds. Let me back to this thing: quantum cohomology, singularity theory, geometry of curvature spaces. So in the paper of Cecotti and Vafa, in this TT star equation, we find actually this kind of this type of Frobenius manifolds. So we find Frobenius manifolds coming from quantum cohomology, from singularity theory, from geometry of Hurwitz spaces. So in some sense, actually, look at the examples coming from Cecotti and Vafa, give us some ideas of how to proceed in general with this integrality problem. And that's what I want to do, and I want to present today, okay? So what I said is what we need is to compute the Stokes matrices associated to the star equation and show the integrality. That is the problem 1 and problem 2a. I already said that. Okay, from a mathematical point of view, this problem had been studied actually by Martin Guess, Itz, and Lin, and also by Takuro Mochizuki and Takuro Mochizuki and Guess, Itz, Lin. They studied the problem from the point of view of TT star equations, and also this problem had been studied by Marius van der Put and myself from the point of view of Frobenius manifolds. So what we did actually with Marius van der Put was to compute some examples, and the talk today is kind of extension of the previous work I made with Marius. Okay, so today I will discuss how to make this computation by the so-called Monodromy identity method, because that was the method we use with Marius van der Put for computing the Stokes matrices. In fact, what we did with Marius van der Put, we compute the Stokes matrices for projective spaces. We gave another proof of the Dubrovin conjecture. And now what I want to propose here is that we can extend that method of computation to other cases. And I will explain why I think that will be the case. Okay, good. So I start with the Frobenius manifolds. I went to physics, and now I want to go to somehow differential Galois theory to say how to use somehow this monodromy identity, what this monodromy identity is. So let me start with this theorem, so the formal classification of differential models. I also have to say that I use somehow in a free way the words connection, differential equation, matrix differential equation, D-module, and differential modules. For me, they are the same things. I am working over a differential field, so there is a good way to go from one to other concepts. So when I say differential module, I'm thinking on the connection and also the differential equation in the matrix or scalar form, right? So there is this very classical theorem in the differential for the classification of differential models. So if you have a differential model of finite dimension, essentially you have a differential equation. That's what this means. Okay. So there exists a field extension of these fields of here, and there is some elements such that actually when we take this tensor product, so we get the differential model and we tensor with this extension. So this differential model decompose in this form, and this actually this part here, which is actually related with this data, they are these one-dimensional models which satisfies actually this differential equation here, and these are just differential modulus with regular singularities. What is the meaning of this theorem? So you have a differential equation over a field, but maybe you cannot decompose the differential equation in that field. So you need some extension. So this kind of the Galois theory for polynomials. So you have a polynomial over a field, and probably you don't have the composition of this polynomial. You don't have all the roots over this field. So you need to take some extension of the field, and then you can find an extension of the field. And if you consider, now the polynomial over this extension, so the polynomial decompose in linear factors in that extension. That is actually the idea of this story, but put it in the setting of differential equations. So you always can find an extension of this field where actually the differential equation decompose in a very nice way, right? That's the idea. That's the idea. Level 13. Perfect.
I'm a little perplexed by the vocabulary. What's a regular singular module?
Okay. This means actually that okay. This means actually that the singularities of the differential equation are regular, logarithmic. So that's mean like for example, like for example, like the case of Picard-Fuchs equation. So you take a Picard-Fuchs equation and you look at the regularities of this differential equation. They are actually regular in the sense that they are logarithmic. They are not pole order, higher order. That's the point, right?
Okay.
That's the meaning. Exactly.
Okay.
So somehow the regular part is contained in this data somehow. That's the idea, right? So there is some kind of regular part, and you can have this other part. That is meant for regular singular, right? Differential model. Yes. Okay. So okay. So what is B here? So B here, this B here is actually is called the ramification index. And somehow the question, if B is equal to 1, this means you don't need to take any extension. So if the differential equation already decomposed in here, so you call this unramified. But if you have somehow the higher ramification in this index, this means that B is equal to the order of the equation. We call that actually this B module can be seen, this differential module can be seen as a differential equation. So if you write this as a scalar equation, so you can see as a differential polynomial, and you see that the order of the equation is the higher order of the derivative. If this is actually this order actually is this B, so you need to take that extension. So this is the totally ramified case. So we have in the two extremes. So you don't need to take an extension, and you have to take the extension of the higher highest degree you can take, right? That's this and that actually is the important cases for me today. And you have this equal to 1, and you have this totally ramified case. Why we are interested in this? Because this equation I defined here for the Dubrovin, for the Frobenius manifold, here, this is always unramified. This is unramified equation. That's the point. So this is always unramified. So you don't need to take any extension for the Levy-Ritching theorem. That's the point. That's why, and then I will say why the totally ramified enters to the game. Perfect. So these Q are actually called generalized eigenvalues, but in the case of the Frobenius manifolds, we have actually they're easy to compute because they are the eigenvalues of the multiplication by the Euler vector field. So in the case of CPN, so you just need to compute the eigenvalues of these matrices. And if you compute the eigenvalues of these matrices, you get these values Q here. In general, for the differential equation, it's not that easy. So you need to actually compute by using the Newton polygon, etc. But for those equations coming from Frobenius manifolds, how for those equations coming from this geometry, these elements here are easy to compute because the information of them is encoded in the matrix multiplication by the Euler vector field. In the case of CPN, by the multiplication by the first chain class. Good. And then actually, as I said, the question coming from the first structure connection of a Frobenius manifold is unramified. But what is the important point here is that, okay, the equation is unramified, but if we make a very easy change of variable, I can get this unramified equation, and the equation became totally ramified. So in these cases, in some of the cases, at least in the cases I want to consider here, if you take this unramified equation, there is a kind of change of variable, an easy change of variable to get this totally ramified equation. That's the important thing. And why we need this totally ramified? Because we can apply this monodromy method that I will explain in a second to this totally ramified equation. And then if you want to get the answer for this, you just take this in account the change of variable, and then you can recover the Stokes matrices for these cases from the Frobenius manifold of these things. So let me introduce some kind of a special Frobenius manifolds. If you look at the case of the CPN, if you look at this matrix, you compute the eigenvalues, for this case, what you get actually is that they are roots of unity. So that's really good. So they are located in a circle. And actually, this is what I want to call set n symmetry. So you have the symmetry of the group of root of unity. You want this the symmetry of the polygon determined by the roots. So I will call this case a set n symmetric Frobenius manifold. So a Frobenius manifold is called set n symmetric if the eigenvalues of the matrix multiplication by the Euler vector field are nth roots of unity. So for the case of CPN, that's the case. And for many of the cases of Frobenius of many of the cases of Cecotti and Vafa, this is the case. So we have this, when you compute the matrix, the eigenvalues of the matrix multiplication by the Euler vector field, what we get is actually a root of unity. This is what I am saying here. And actually this terminology, this terminology for Frobenius manifolds comes actually from the fact that in Cecotti Vafa, they call this set n symmetric models. They call this set n symmetric theories. So the theory which actually satisfy this property. Okay? So I am using this terminology just to define these Frobenius manifolds, and this n actually is emphasized in the fact that we have this n root of unity as a set of generalized eigenvalues of the quantum of the multiplication by the Euler vector field. Right. And then we have the first proposition is if we have a Frobenius manifold of this type, so there exists a change of variable such that we can actually take the unramified equation and make it totally ramified. So in the case when you have this property for the eigenvalues, so the unramified equation, I defined this first structural connection, actually becomes totally ramified used by an easy change of variable. That's something we can do. And then now because we have this totally ramified, we can actually try to use this monodromy identity. I will explain in a second. So any questions so far?
I think we're good.
Okay, perfect. So now let me say what the monodromy identity is. So now you consider this Q of the generalized eigenvalues, and then you want to study this, the solution, the asymptotic solution. So you want to see how the solution behaves when you cross some Stokes direction, and then you have to consider this difference. So you have to consider the difference between these generalized eigenvalues. They are actually series. There's a series in set. And this is a sum, actually. This is this expression in set when actually I is different to j. And Stokes actually direction is given by this property here. So the Stokes direction somehow are the direction we want to consider to make the sectors where actually the asymptotic behavior of the equation change. That's the role of the Stokes direction. And there is this other direction which are called the singular directions or anti-Stokes directions, right? And that's the ones I want to use for computing the Stokes matrices. This is actually, if you look at the literature, some people actually use directly the Stokes directions, but for me, it's easier to consider the anti-Stokes, but there is no actually, I mean, for the goal of today, it's not really important to enter in this distinction. So the only thing you have to consider is that you somehow, I mean, morally, what you have is you have you have the plane decomposed in sectors, and you want actually to, and this decomposition actually is given for some rays and some Stokes, and we call this a Stokes direction because when we want to consider the asymptotic behavior of the equation, so we need to actually these sectors actually are the boundaries of the sectors we want to study the solution of the differential equation. That's the point, right? And that directions are actually given by this information of the generalized eigenvalues. So okay, and for any singular direction you can construct the Stokes matrix, and the monodromy identity is the following theorem. So you have this singular direction. There is always finite directions, okay? then what you have is that you take the product of this Stokes matrix associated to any direction, and the formal monodromy. This is actually conjugated to the topological monodromy. And in the case we are considering, the topological monodromy is easier because it's just the monodromy at zero. You know, we have this equation with two singular points. So it's regular point at zero and some irregular point at infinity. At zero is regular point, so you can compute the monodromy, okay? And you get the matrix. So the interesting thing is that you compute this matrix. So this matrix is actually conjugated to this product, the Stokes matrices. So this means actually that you can, in particular, they have the same characteristic polynomial. So if you compute this monodromy at zero and compute the characteristic polynomial, and then you compute this product, even you don't know what are these matrices, and then you compute this product, and then you compute the characteristic polynomial, and then comparing the coefficients of the two polynomials, you can get the values of the Stokes matrices. That's the point. And the good thing is that in the totally ramified case, you can do it in a very precise way, and you can get the full information of the Stokes matrices by knowing the characteristic polynomial of the monodromy at zero. That's what we did with Matt Derput and for the case of projective spaces, and that's what I want to propose for other set n symmetric Frobenius manifolds. That's the proposition I have here. So for the totally ramified equations, the Stokes matrices are fully determined by the characteristic polynomial of the monodromy on set equal to zero. So if you know the monodromy at zero and you compute the characteristic polynomial, this is just a linear algebra problem. Then we can compute the Stokes matrices for the totally ramified equation. And with Butterpool, we did for projective spaces, for weighted projective spaces. And in general, for other set n symmetric Frobenius manifold, that's somehow work in progress by myself. But it's true that we can do that. That's the point. And there is this theorem. So this theorem actually was found independently by Takura Mochizuki, and also in some special cases by Marius van der Ploeg and myself. And I have this extension for the set n symmetric Frobenius manifolds, and the theorem said, okay, if you have the equation coming for the first structure connection of a set n symmetric Frobenius manifold, so you say that this manifold has an integral structure if and only if the coefficient of the characteristic polynomial of monodromy at zero are integers. Why? Because this means that if the coefficients are integer, so this means that because of this property here, the entries of the Stokes matrices are integers, right? And in a very informal way, we can define a integral structure in the Frobenius manifold as the property of having Stokes matrices, integral Stokes matrices. That's the point. So this somehow theorem, in some sense, characterize some Frobenius manifold with this integrality property. The problem is that actually there is no explanation of why this integrality should appear in this context. And in the in the 10 minutes I have, I will try to discuss that problem. What the integrality would mean. The second part of the second question I asked at the beginning. So here we have some interpretation. So we have integral Stokes matrices means that integral Frobenius manifolds means that you have these Stokes matrices with integer entries. The problem is that what is the meaning of this situation? So why we have to expect this kind of property for the Frobenius manifolds? And that is the content of the last part of my talk. So some questions so far? Any questions?
I think we're good.
Okay. Perfect. So let me go to the case of quantum cohomology. And I will back to this semi-simplicity stuff in the quantum cohomology case. So the Dubrovin conjecture actually is very, for me, actually amazing conjecture about the semi-simplicity of quantum cohomology and the right categories of coherent chips. So Dubrovin actually started this conjecture in his ICM talk in 1998, and the conjecture said that, okay, you have a manifold, Fano manifold, so the quantum cohomology is semi-simple if and only if the derived category of coherent chips of the manifold has a full exceptional collection. And this is very strange in the sense that, so we are related this topological geometric information about the manifold, this quantum cohomology, but we also have this categorical information about the manifold, and actually they are connected in a very nice way. I think actually this Dubrovin conjecture should follow from homological mirror symmetry. Probably this homological mirror symmetry proposed by Kontsevich will be the explanation of this Dubrovin conjecture. We want actually to find a conceptual approach to the Dubrovin conjecture. Probably we'll have to look at the homological mirror symmetry. So far, there is some proof of this conjecture for projective spaces, Grassmannian, some Fano trifolds, but there is no conceptual approach. What we do is we compute the quantum cohomology, we look at the semi-simplicity, and then we compute the derived category coherent chips and show that there is an exceptional collection, and we say, okay, that's good. It's support for the Dubrovin conjecture. But there is a deeper relation, which is related to my talk today, is that actually there is some relation between the Stokes matrices for the quantum connections with this first structural connection and the grand matrix for the full exceptional collection. So you have these objects in the full exceptional collection, and you compute the matrix given by the dimension of the X groups, and you give these numbers, and these two matrices actually match. And that's actually one reason we have this integral Stokes matrices for the semi-simple case, because these grand matrices are integer because they are dimensions of some vector spaces, essentially, right? So that's somehow the reason of the integrality. Somehow the Dubrovin conjecture said that you can capture the idea of the integrality by studying this derived category. That's the important message here. So you have this derived category, in some sense, control the information about the quantum cohomology, because it says if it's semi-simple or not, and also say how the Stokes matrix should looks like. Actually, that's the important thing. So there is this derived category controlling this information about the topology of the manifold. That's very interesting fact. And it also happens. It happens only it only happens in the case of semi-simple. So you have, for example, Calabi-Yau case. In Calabi-Yau, there is no point to consider Stokes matrices because you don't have a Stokes phenomenon at all. But still, even if you don't consider this part, so if you consider the derived categories of coherent chips for Calabi-Yau manifolds, they don't have full exceptional collections. That's the point, right? So that's why semi-simplicity is important. Good. So now let me formulate by using this conjecture by Dubrovin for the quantum cohomology to formulate a very vague conjecture. Actually, I should write here expectation. It's more than expectation. It's more an expectation than a conjecture, in fact. But okay, let me put it in this word conjecture because that's the LaTeX word I have for this thing. But it's very vague. I mean, it's more an expectation than a conjecture. Okay. So now just not consider Frobenius manifolds coming from quantum cohomology, you consider actually a generic semi-simple Frobenius manifold with this property, with this integral structure. This means that consider a semi-simple Frobenius manifold with integral Stokes matrices. So the conjecture I want to formulate is that there exists actually a derived category, in this case, the category of representation of certain quiver, such that the Stokes matrix associated to the first structure connection equals to the grand matrix of the full exceptional collection. And you can ask why representation of a certain quiver? Because if you look at this case of the quantum cohomology, so there is this all resolved by Bondal and the Russian school that the derived category of coherent chips, so finite manifold, if the category has a full exceptional collection, so you can construct a quiver out of the exceptional collection, and you consider the derived category of representations of that quiver. The quiver can have relations actually. So there is this equivalence between these categories, between the categories of the coherent chip of a finite manifold and some quivers. And for this theories coming from physics, these Cecotti and Vafa cases, we can actually construct some quivers too. And that's actually the candidates for the quivers here. So what I believe is that if you consider those quivers associated to these theories, and in some sense you said, okay, if the quiver are associated to these supersymmetric theories, you can associate the quivers to the Frobenius manifold. So if you take the direct category of representation of those quivers, so the grand matrix for them that should coincide with the Stokes matrices for this case, and this is because this is semi-simple Frobenius manifold. So what this conjecture actually says is that the integrality of the Frobenius manifold is captured by the behavior of some direct category naturally associated to the Frobenius manifold. And this kind of this very vague conjecture is kind of extension of the Dubrovin conjecture. So the Dubrovin conjecture is just for quantum cohomology case, and what I want to propose is something which is far from the quantum cohomology and consider another semi-simple Frobenius manifold. Okay. So I think that actually the symmetric Frobenius manifold I discussed today should provide test cases for the conjecture or the expectation. So I think that this conjecture, so as I said, actually is my attempt, as an attempt to understand the meaning of integral structure for Frobenius manifolds. But I also mentioned at the beginning that there is some relation with some conjectures which are called gamma conjectures. So let me say something about gamma conjectures. So gamma conjectures actually are some refinement of the Dubrovin conjecture. And this refinement of the Dubrovin conjecture was actually proposed by Golichev, Galkin, and Iritani. And what they say is that if you study the asymptotic solution of the differential equations, for the quantum differential equations, in the case of quantum cohomology, so you can construct some characteristic class for the finite manifold. And that characteristic class actually is given by what is called the gamma class. So the gamma class is actually some expression using the gamma function, and then you expand this somehow, this gamma function using some chips. And actually, the information actually for the gamma class you get actually comes from the derived category of the underlying finite manifold. So how that's the content of these conjectures, and actually they explain integrality in that sense. For them, the integrality comes from the fact that you can actually construct this characteristic class. So the idea is that if you use mirror symmetry, this gamma conjecture also works for the Calabi-Yau case. So that's also the point. In some sense, you can, but because this integrality, what they study actually is that if you use this mirror symmetry, and you consider mirror symmetry as relation between Hodge theory and Gromov-Witten theory, what Iritani proposed was, okay, in Hodge theory you have a lattice, an integral lattice, and then using mirror symmetry, what he wanted to do was to construct an integral lattice for the Gromov-Witten theory. That's, I mean, very informal ways what is going on. And then this integral lattice in the Gromov-Witten theory is actually related with this gamma class. And the existence of this gamma class and this relation between these integral structures and mirror symmetry is the content of gamma conjectures, right? These conjectures have been proved by Iritani and Golichev and Galkin for the case of projective spaces and also for Grassmannians, but for other cases are still open. There is a work by Golichev and Saguier for some threefolds. They also compute some parts of the conjecture for some final threefolds. Okay, and let me finish with this discussion of how this is related with the Hodge structures, the non-commutative Hodge structures of Katzarkov, Kontsevich, Pantev. Is because actually this semi-simple Frobenius manifolds, actually this first structural connection for semi-simple manifolds should provide examples of the non-commutative Hodge structures in the sense of Kontsevich and Pantev. So this non-commutative Hodge structure can be thought as generalization of the Hodge structure. So usually in Hodge theory, you just consider Picard-Fuchs equations with regular singularities, Gauss-Manning connection, etc. But now this non-commutative Hodge structure extends this setting to consider equations with irregular points. In particular, we expect to study the first structural connection for semi-simple Frobenius manifolds from the point of view of this Katzarkov, Kontsevich, and Pantev. And this actually allows me to formulate the second Bayes conjecture, and I will finish with this conjecture that says that actually this set n symmetric Frobenius manifolds I am proposing today with these integral structures should provide examples of non-commutative Hodge structures of exponential type. The exponential type means unramified equations with irregular singularity of polar order 2 and integral structure. But also this non-commutative Hodge structure, these are special in the sense that they are unramified, but they become actually ramified, totally ramified by interested or easy actually change of variable. So to finish, actually, I would say that the goal of this project is to understand the integrality property for these manifolds and look at for me the first and natural example of this situation, which actually is this set and symmetric Frobenius manifold. So thank you for your attention. I think I can stop sharing.
Hi, Enrique. Are you there? I think that Enrique has one problem with the.
See, because it's yeah. And now Enrique is here.
I'm here. Can you hear me?
Yes, I can.
Okay, so do you have any questions, please? Well, I do.
Okay.
So what stops you from defining the sort of analog concept of Frobenius manifolds for say Cecotti manifolds, which are just transversely complex?
Yeah.
Could you do the same for Cecotti manifolds?
Okay, but I think that probably in that case, probably this case is close to is closer to the Calabi-Yau case, and so I guess we can actually get this Frobenius manifold, and this Frobenius manifold should be closer to the Calabi-Yau. So I guess probably let me make this very vague conjecture again. I think that they should be non-semi-simple. I will expect that the Frobenius manifold for the Cecotti will be non-semi-simple. That's what I expect.
I don't even mean manifolds which are contact Calabi-Yau. They don't have to be.
Okay, general.
I mean Sasaki in general.
Okay, okay, good. Okay, okay.
Right? You could.
Yeah,
You
I think, okay, right. I mean, I think probably we can actually try to define this analog of the first structure connection.
Yeah, it should work.
And when you get this, yeah, I mean, and that's good question actually, because I know, I mean, semi-simplicity is not just a condition of the Fano manifold. I mean, you can actually get this. There is non-Fano example because actually semi-simplicity is preserved by blow-ups. So in particular, if you take P2 and to take P2 and blow up to more than 9 points, you get something which is not non-Fano, but it's also semi-simple. And there is this other result that the existence of full exceptional collection is also preserved by blow-ups. So there is non-Fano examples where you have semi-simple Frobenius manifolds and full exceptional collection. And probably that's a good question. Probably one's source of examples will be Cecotti manifolds. We can get this kind of a very appropriate definition of the Frobenius manifold, and we can get all this data. We can describe all this data. Probably we can get this semi-simple thing and look at if there is some kind of extension of the growing conjecture for the setting. I mean, for me, at least for me, the question makes a lot of sense. So that's a good question. I mean, I haven't actually looked at the case, but it's something we cannot really. I mean, I guess it's something we should actually discuss.
Yeah, that's found in our discussion list.
Yeah, that's kind of
extension
of the discussion we have. It's completely natural question. Perfect. I completely agree. That's a natural question.
Any further questions, everyone? Well, if not, then let's please thank Alex again.
Okay.
And Andres, who's our speaker next week?